Hello again, everybody. Let's continue our discussion on general motion. Right now we're going to look at rotation about a fixed axis. And we want to talk about a couple of different things. And what we want to start talking about are some terminologies. We want to look at the idea of position, displacement, velocity, and acceleration. We've talked about this a little bit in a previous video, but I want to go through it again. So let's take, for example, this wheel, right? And I've got this thing rotating. You can see this piece of tape over here. Let's put the piece of tape right there. So it's kind of in the horizontal position, positive x-axis, if you will. And I'm going to rotate it counterclockwise. And so when I do the right-hand rule, curl my fingers in the counterclockwise direction, my finger points away from the wheel, right? And we're going to call that the positive z-axis. Okay, so the unit vector in that direction will be k hat, right? And I want to talk about a point here on the wheel, call that point A. Might not be able to see those, but then another point, and that's point B. We'll get to that here in just a second. Okay, so as I rotate this wheel in the counterclockwise or the positive z direction, this line is undergoing a change. So right now it's at the positive x-axis, which is 0 degrees or 0 radians. As it rotates, I'm going to go up here. Maybe that's 45 degrees, which is what? Pi over 4 radians. Right, there's 90 degrees, pi over 2 radians, etc. There's pi radians, right? 3/2 of pi radians. And then finally back to where I started from, which would be 2 pi radians. So there's been some amount of angular position. This has gone from this angular position all the way around to other angular positions until it finally returns to where it was at in the beginning. Although we'll say that the displacement, if you will, was 2 pi radians, right? So what is position? Position then is an angular measure from some sort of a reference point. I've called it the positive x-axis. Here, it doesn't really matter. If I start here and I consider that 0 degrees or 0 radians, and then I rotate through here, I've gone through 45 degrees, ballpark, or pi over 4 radians. Right, so my position here is 0, my position here is pi over 4, my position here is pi over 2. Right, so those are angular positions, right? And we use the same terminology. I've got translation, I talk about positions, and when I've done that in the past, I may have used an R for that in 3 dimension, or just an X in 1 dimension. That was the translational position, right? R in 3 dimensions, X in 1 dimension, R also in 2 dimensions. The displacement would be delta R, vector quantity, or if it's only 1 dimension, delta X, although it's positive or negative, right? Depends on what you consider to be the positive direction. We're going to have an angular position, and we're going to use the Greek letter theta for the angular position. That's what we've used for angles for a long, long time in math courses and in engineering courses, right? Theta is my angle. So if my 0 point is here, and I pass through 45 degrees, then I have an angular position now of 45 degrees or pi over 4 radians. Okay, so there's an angular position. If I want to consider this a vector quantity, then I'll use the right-hand rule, and my angular position will always be measured in the k direction. Usually I don't worry about that too much, but we can. And so we'll consider that angular position to be in the k direction, right? Well, then there's an angular displacement, and not too surprisingly, that's just delta theta. That would be the angular displacement. All right, then it can be rotating at some speed. That's relatively fast. I might rotate it at a slower speed. Ooh, that's not really balanced, is it? Let's go with that one as a slower speed, and then that one's a faster speed, right? So the angular velocity is different. Well, we're going to define angular velocity the same way we did translational velocity. So this was the derivative of r with respect to time, or in 1 dimension, the derivative of x with respect to time. And these were equal to velocities. Right? In this case, that velocity is a vector quantity. Over here, we're going to have an angular velocity. All I do is I put the word angular in front of my rotational parameters. So the angular velocity is the derivative of theta with respect to time. And I generally use the Greek letter omega for the angular velocity. Theta is measured in radians, time is measured in seconds, and so this will generally be in radians per second. Radians is dimensionless, no mass, no length, no time. And so this is also equal to seconds to the minus 1. Both of those are legitimate. I like to do radians per second just to be more specific, but I don't have to. Seconds to the minus 1 is understood to be radians per second in the case of angular motion, right? Not surprisingly then, acceleration is the second derivative of r with respect to time, or the derivative of velocity with respect to time, right? We refer to that as the acceleration. And then similarly here, the angular acceleration, right? Just put the word angular in front of it, is the second derivative of theta with respect to time, which is the derivative of omega with respect to time, which is alpha. So we use the Greek letter alpha for the angular velocity, okay, or the angular acceleration, excuse me. So alpha is the Greek corresponding to A, right? Omega is not the Greek corresponding to V, but that's all right. So we use alpha for the angular velocity, okay? And so there's my relationships between translational parameters and rotational parameters. Again, all I do is I put the word angular in front of it, and it's all the same stuff. All right. So next go around, we want to take a look at how does the position of A and the position of B relate to this in translation, right? In 2 dimensions. How does that relate to the angular position of the white line? Okay, so we're going to talk about that next video. Any comments or questions, please leave them in the comments down below, and I'll get back to you as soon as I can. Thank you.